win or you die, right? Okay. Too much? Okay. All right. Welcome to Too Much Chem. I'm Johanna Brown. I sometimes occasionally teach chemistry at the high school level. It's really digressed, hasn't it? So today is all about molecular geometry. And in order to do this, you need to have a really firm understanding of writing Lewis structures. So if you're not quite there on Lewis structures, please go practice that, come back, and then we will do this. All right. So with molecular geometry, we got to start with these Lewis structures. So let's just think about Lewis structures for a second. Why are they great? Well, they allow us to communicate how molecules are connected, so what atoms are bonded to each other. We're able to figure out where there might be double bonds, where those lone pairs of electrons are, all of that. So they're really nice for that. One issue, though, is that Lewis structures exist in a two-dimensional world, and we live in a 3D one. So we need a way to get Lewis structures off the page to help us think about the actual shape of molecules. Luckily, we have a way to do that, and that's what we're doing today, right? So our first example today is going to be methane, which you should hopefully be familiar with. We have a central carbon with 4 hydrogens bonded around, covalent bonds, nonpolar. And so when we think about this molecule, do you think that this is what it actually looks like in real life? Do you think it has these 90-degree angles and it's just like that? Think about it for a second. Okay, hopefully you've thought about it. So now let's dive in. What are these covalent bonds made of? Well, electrons. So we have pairs of electrons here making up the bonds. And what are electrons going to do to each other? Well, they're all negatively charged, so you should expect them to repel. So if we were expecting these bonds to repel each other, do you think they'd have this shape or something different? Hopefully you're thinking something different. And this is what it actually looks like. Okay? So this is our methane molecule, and notice the hydrogens are all as far apart as they can possibly get, all right? So when we look at these, we see that the electrons that make up these bonds are repelling each other, so they're all equally far apart. We call this VSEPR theory, or valence shell electron pair repulsion theory. I can do it. You can too. And I know I had some students last year who like to say VSEPR, but we pronounce it VSEPR theory. So you need to remember, whenever we're talking about geometry, we're imagining that these electron pairs are all pushing on each other to get as far apart as possible, right? So once you imagine the shape, we actually have names for these. The name for this shape is called tetrahedral. And the way I remember it is that there are 4 bonds, and then we get tetra, 4. So tetrahedral is the shape of our methane molecule. Let's go over to ammonia. So what's going on here? We have 3 bonds and 1 lone pair. Do you imagine that these will all repel as well? Hopefully. So these shouldn't act really too much differently than these here, but then we have that lone pair, okay? So this lone pair will also push on the covalent bonds, just like this bond did over here in methane. Here is our nitrogen molecule. So you'll see we have these 3 hydrogens bonded, very similar to our methane, but then up top, we instead have that lone pair. So you don't see anything bonded up here, but that lone pair is still exerting a force on all of the electrons in these bonds here. So we end up seeing a shape that we call pyramidal. Okay? So it actually kind of looks like a nice little pyramid. We don't have another atom up here, but those electrons are still forcing these to be down a little bit. Okay, so the bond angle that we actually see between the atoms here is 107 degrees compared to the 109 degrees that we saw in our tetrahedral molecule. And that's because that lone pair of electrons sit a little closer to the nitrogen on top, forcing these together more than we see the hydrogens being forced together in methane. Okay, so tetrahedral for methane, ammonia is pyramidal. Let's go on to our next molecule, formaldehyde, which you might remember from your biology class if there were jars of brains or anything in it. That's why I teach chemistry. So formaldehyde, we've got a double bonded oxygen to our central carbon and then 2 hydrogens. So again, do you think you'll see 90 degrees here? I hope not. I hope at this point we're thinking, wow, there are electrons here. They're definitely going to be pushing on these electrons, which will also be pushing on those electrons. So what sort of shape do we see? And what do we do with a double bond? Well, what we end up seeing is a molecule that looks kind of like this. So you'll notice we have those two hydrogens and then the double bonded oxygen, and they are all equally far apart. That's actually 120 degrees there for all of the bonds. And those double bonds, we consider them being all the electrons in that being in the same, what we call a domain. So they're in the same area, the same region. So they kind of act as one set, okay? So these will repel those the same as if this was just a single bond, okay? So notice this is all on a plane, and that's where it gets its name from. This is called trigonal planar. Trigonal, we have 3 domains. Planar, because there's a plane that bisects this, okay? So that is formaldehyde, it's trigonal planar. Let's go on to water, one of a chemist's and biologist's, really any scientist's favorite molecule, I hope. Notice here, we have 2 lone pairs now, 2 covalent bonds. So what's going on here? You might have seen your chemistry teacher draw water like a certain mouse that we're all pretty familiar with. So why do we draw it like that? Well, we have a lone pair, another lone pair, our 2 bonds. Those are all going to repel each other, which is going to cause water to look something like this. So here's our oxygen, here are our hydrogens, and we're imagining those lone pairs up there. This is a very visual, thoughtful concept. So if you're really a hands-on person, make sure that you get some models from your teacher or look at models online that you can move around so you can really get it into your brain. Okay, so here's our water, electrons up here, electrons up here. They're kind of forcing those hydrogens together that are bonded to the oxygen. We're going to see a bond angle of 104.5. We call the shape bent, which I think is pretty self-explanatory. So if you have 2 bonding domains and then lone pairs, we'll call that bent because it'll make that nice shape. Okay, let's get to our last one. Our example is carbon dioxide. So let's see, hopefully you're feeling more comfortable. How many domains do we have here that electrons are in? Well, I see 2. And this is one where the Lewis structure is actually pretty close to what we're going to see 3-dimensionally. We have 1 domain here, 1 domain here. When they push on each other, what is that bond angle going to be? Well, 180 degrees. So let's see that 3-dimensionally. Here's our model for carbon dioxide. We have a carbon in the middle and then 2 double bonds on either side. The name of this shape is linear. Okay, which I also think is pretty self-explanatory. So as you go on to apply this concept, what do you need to know? Well, what you need to know is the names, how to get from the Lewis structure to the shape, and then the bond angles. So when you have 4 domains, that's tetrahedral, okay? When you have 3 bonding domains, 1 lone pair, we call that pyramidal. When you have just 3 bonding domains, that's trigonal planar. When you have 2 bonding domains and then lone pairs, we call that bent. And when you have just 2 bonded domains, that is linear. Again, please go out and practice this, work with models, process through it. Okay, next week we are going to be working on polarity and see how this applies to molecular shape so we can even better understand how covalent compounds work together. So this has been another episode of Too Much Chem. Make sure to subscribe. I'll see you next week.